Good morning, good afternoon, everyone. So I'm Marc from Euresys and Sensor to Image. Let me start with a quick company overview. At Euresys, we manufacture machine vision components. This is mainly a set of frame rubber cards that are compatible with co-express over fiber, camera link, and analog cameras. We also design and sell a set of machine vision software libraries that are called the inVision tools. And then today we are going to talk about our IP cores with our subsidiary in Germany called Sensor to Image. We are designing and selling a set of IP cores implementing the major machine vision interfaces, GigE Vision, co-express over fiber, and USB 3 vision, as well as interfaces to imaging sensors such as MIPI CSI2, for example. With this IP core, you can really speed up the design of your embedded vision system. And this is what we are promoting here. These transport layer IP cores are not just sold alone, but they are sold along with the support services and development kits to help reducing product development phase and the time to market. So today we are going to focus on one of these IP cores, which is the GigE Vision IP core. In two words, an IP core is logic or software for an FPGA. An FPGA is a field programmable gate array. This is a highly programmable electronic component. Our GigE Vision IP core is compatible with AMD Xilinx or Intel Altera FPGAs, and we are also developing compatibility with the Microchip PolarFire family of FPGAs. Our IP cores are compact. They are highly customizable because they are meant to be integrated into your application. In particular, the GigE Vision IP core supports speeds from 100, of course, but including 1 gigabit per second and 2, 5 gigabit per second and 10 gigabit per second transfer, and even more, and that's the topic of the presentation. All our IP cores are delivered with a full-featured reference design, and this will help me explain a little bit more about how we deliver our IP cores. So the IP core in itself allows you to define the contents of an FPGA, the field programmable gate array. It is a set of files that describe the logic, and the language behind it is called VHDL. The VHDL files describe the logic of the FPGA inside your system. The FPGAs we use also have an embedded CPU, so we also provide with the C code that goes into that CPU. Along with the development tools that are provided by the FPGA vendors, then you will be able to compile all these files, customize them to your application, and generate the contents of your FPGA. During the development process, you are going to use a development kit such as our machine vision development kit. And here we see a photo on the left of the special version of our MVDK for GigE Vision development. You can see that it accepts a daughter board containing the FPGA. This is at the center of the development kit. And then it also can be connected to different kinds of interfaces through the use of specific FMC modules. Of course, this development kit does not look at all like your final product. And we mostly sell our IP cores to two types of customers. Type number one is camera developers, camera manufacturers. Our IP cores are actually used by major camera manufacturers here. And then you see that by the use of our IP core, you will be able to reduce the size of the entire design into a much more compact camera. But we also sell our IP cores to embedded vision system developers, designers. many different kinds of embedded vision system. They can be dedicated to image processing, they can be dedicated to image transfer, and on the bottom right of the slide here, we see a typical design that either our customers, or in this case, we have designed, and including our IP core. The next part of the presentation here will focus mostly on the GigE Vision standard and what we have been developing around streaming. So GigE Vision is a communication in vision application, and I would even say for machine or computer vision applications, and it is based on the Ethernet technology. It supports any transport speed and any transport media which is within the Ethernet standard. It uses the UDP protocol as the low-level transport protocol. GigE Vision defines separate communication channels for control, messaging, and for streaming data, streaming video. And GigE Vision is developed and maintained by the GigE Vision Technical Committee. It's also covered by the A3 Vision and Imaging, the former AIE. Let me come back to the second point here, is that the fact that GigE Vision and Ethernet support any transport speed and transport media included within Ethernet. And this gives us a lot of possibilities here. Ethernet is a really wide international standard defined by this IEEE standard we see here. When we think about a GigE Vision camera, we mostly think about a camera with an RJ45 connector and then a Cat5, Cat6 twisted pair cable running at 1, 2, or 5, or 10 gigabits per second. But actually, there are many, many other possibilities. And we start seeing 10 GigE cameras on the market, for example, using SFP plus cages. SFP plus transceivers are able to convert electrical signal into light and connect to fiber optics. This is a great option here that allows us to use fiber optics and extend the speed from 1 to 10 gigabits per second. But we can see on the table on the right that Ethernet also supports a wide variety of connectivity options, starting with QSFP plus at 40 gigabits per second, QSFP 28 at 100 gigabits per second, and so on. So we think that this is a great opportunity here to expand the bandwidth of our connection. And we have a demand for that. We have a demand for multi-gigabit Ethernet video streaming. Why? Because there are more and more high frame rate and high resolution image sensors available. High resolution image sensors that need more than 10 gigabits per second. There's also some demand for multi-source cameras and 3D cameras that need more data to transfer. Another application case, mostly for embedded vision systems, is the request to aggregate multiple lower speed streams into a single high-speed stream connected to a host. This is a standard request that we have from our customers too. So based on this request, we have started to investigate the use of higher speed streaming. So what are the current limits of our GigE Vision IP core? First, the GigE Vision IP core that we provide has been extended to support 64-bit data paths. So this means that if we want to operate, for example, at 25 gigabit per second Ethernet, we require a clock of just below, actually, 400 megahertz. This is easily achievable using higher-end FPGAs. But anyway, for that kind of system, we need that kind of FPGA because we need the 24 gigabit per second transceivers anyway. However, we have seen that when using the UDP protocol defined by the GigE Vision standard, this is the limiting factor. This is not the limiting factor on the GigE IP core side, because the protocol itself is implemented into an FPGA, so there's no problem working at a higher speed. However, this is the limiting factor on the PC-based receiver application side. From our experience, we see that when using UDP, we can easily run at 1, 2, 5 gigabit per second, no problem. UDP starts to show its limits at 10 gigabit per second and can be improved a bit by using specific filter drivers, but not going much further than that. Using TCP provides improved performance for the cost of increased latency, but the real good option here is to switch to a different protocol called RDMA. So what is RDMA? RDMA stands for Remote DMA. DMA is direct memory access. And one way to use RDMA is to switch to a protocol which is called RoCE v2. RoCE v2 stands for RDMA over Converged Internet version 2. RoCE v2 is part of a much wider specification, which is called InfiniBand, the InfiniBand architecture specification. And it defines how to run this InfiniBand specification on an Ethernet infrastructure. This is exactly what we need here, because we have an Ethernet infrastructure, because GigE Vision is based on Ethernet. A lot of advantages come with the use of RoCE v2. It offers hardware offloaded data transfer using standard cards, which means high performance, low latency, low CPU load, high efficiency, and reliability. So we have studied to implement and experiment with the use of RoCE v2 at sensor to image. And we have investigated the use of RoCE v2 with a standard network interface. We believe that this is a very important part of the customer experience is to use a standard network card. What we can see is that typically 10 to 25 GigE cards with an optical fiber interface support RoCE. This is the case of the NVIDIA Mellanox, the chipset and the network cards. This is the case of the newest Intel chipsets and network cards. And this is also the case of Marvell and Broadcom chipset. So we think that this is the way to go, and going forward, most of the higher end network cards will support this RoCE v2 protocol. We have also implemented a RoCE v2 device into an FPGA to measure the resource use. And so this table here compares an existing 25 gigabit per second RoCE v2 IP core to a standard GigE Vision 2.2 device reference design. We can see here, and if we compare the first line with either the second or the third one, we can see that our IP core using RoCE v2 uses almost the same type of resources when we count the number of lookup tables and when we count the number of registers. So this is really, really good news. We are not going to need a much bigger FPGA. When we check the number of block ramps, we can see that the RoCE v2 IP core requires much more block ramps, but this is because the buffer is inside the FPGA. So the RoCE v2 IP core does not require an external memory, which is a great advantage here. What is the status of our RoCE v2 implementation at sensor to image? We have a working prototype that has been demonstrated at the Vision show in Stuttgart and in Boston. This was last month. With this prototype, we were streaming at 25 gigabit per second using the RoCE v2 protocol. On the other side, we used a host application running on a Linux PC. This is a detail of the hardware and software that we have used during this demonstration. So the device was an AMD Xilinx Kintex UltraScale FPGA inside this evaluation kit. The receiver was a standard PC with an NVIDIA Mellanox network card. Totally standard also, and the interconnection was an SFP28 transceivers, 2 of them, 1 on each side, linked by fiber optics and an LC connector. The software currently is Linux, but of course we can have a Windows version, and we have designed a Rocky V2 viewer application to receive the video stream. As a conclusion, at Sensor to Image, we propose the use of Rocky V2 as a low-level transport protocol for Ethernet streaming at 25G and more. We have a prototype IP core that will be made available for evaluation during the first half of 2023. So if you need to stream video at that speed, if you are interested in experimenting with Rocky V2 or interested in that kind of bandwidth for your camera or for your embedded vision system design, then please contact us. We are also very active at the GigE Vision Technical Committee. We work along with major partners at the technical committee to continue developing the integration of Rocky V2 within the GigE Vision standard. So we really hope that this protocol will be included into GigE Vision in the near future.